Most P5 questions and papers, they just follow the same pattern, which is that it's more of a common sense paper. You already know chemistry. Like if you're doing P5, which basically means you're prepared for P1, P2, P3, P4. So you kind of know all of chemistry. So you don't have to do any extra preparation for that. Uh, Except for the fact you just need to familiarize yourself with the pattern of the paper, which is a lot of common sense. It's they're going to talk about two experiments. Usually it's two experiments, and
Okay.
both of those two experiments, I mean, there's a very bright chance you have never actually performed those experiments or never actually heard about those. I mean, they can give you any experiment, and you just have to use your common sense. Most of the answers are going to be derived from the information that is given over here. So so the first thing, so read the question carefully. Remember, you might not have done this experiment ever. So every time the experiment is kind of new. So a student is provided with samples of 6 metal carbonates known to be ores of the metals barium. So they're carbonates: barium carbonate, calcium carbonate, copper, iron, lead, and zinc carbonate. And all the ores, they contain carbonate ions, and some might also contain hydroxide ions. So for example, so the first statement is that there is an ore, and let's say it's a barium ore.
Mm.
So what the question states is that it contains barium carbonate, right? And may also contain the hydroxide ion. So it might also contain barium hydroxide as well. But we're not sure. So it might also contain hydroxide ions. So each ore sample is ground up and measured, and a measured mass of the ore is reacted with an excess of hydrochloric acid. The carbon dioxide produced by the reaction is collected over water, and the volume of gas collected. So it's a mixture of barium carbonate and maybe there's barium hydroxide. So when you react it with HCl, what is going to be produced? It's going to be barium chloride, water, and carbon dioxide as well. Now that carbon dioxide is coming from the carbonate in the ore. That's where the carbon dioxide is coming from. So he's collecting the carbon dioxide, and the volume of the gas collected is recorded. Each ore is tested 3 times. Name the independent variable. The independent variable in the experiment is the one that you're controlling. So it's the measured mass of the ore. I mean, you're selecting the mass of the ore, right? And the dependent variable is the one that depends on this. Like if you select a mass of ore, a certain amount of carbon dioxide is going to be produced. That would be dependent on this. So the dependent variable is the volume of carbon dioxide, right? Is that clear?
Yes, sir.
So there are 2 variables. That is, there's a measurement of the mass of the ore, and there's the volume of gas that is collected, which is the dependent variable. Apart from mass of ore, state a variable that should be controlled. So a lot of things have to be controlled, which is that the ore is reacted with an excess of hydrochloric acid. I mean, you change this variable and you try to figure out what happens to the volume of carbon dioxide. All other variables, they need to be kept constant. So what are the other variables? It could be pressure. Because if you change the pressure, the volume of carbon dioxide would be different, right? Is that clear?
Yes, sir.
So and the size.
Which one?
The size of the ore.
That could, but that can be possible, but that will not affect your variables. I mean, you're going to try and keep those variables constant. That will affect your measurements of the 2 things. Is that point clear?
Yes, sir.
I mean, size of the particles would be a variable if you were timing this. Because size of the variable would affect the rate of the reaction, right? But you're not measuring the rate of the reaction. But I'm going to check anyways. But make sure that the variables that should be controlled are those that change or affect your independent and dependent variables, especially your dependent variables. So I think pressure is one, but I'm just going to check. I might be wrong about this part. because it's a very common sense, it's a very general knowledge question. Over here, he's talking about the temperature relating to the collection of the gas, but why not pressure? Let me first talk about temperature. Because temperature is also going to affect the volume of the carbon dioxide gas that is collected. But why not pressure? Wait a second. H4 is measured reactive in excess of hydrochloric acid, is collected over water. So pressure is because pressure is already controlled, because if you're collecting it over water, right?
Yeah.
So it's not if you're collecting or bubbling it through water, the pressure, I think, is already controlled. I mean, that is, I think, what he means, because the pressure is already controlled because you're collecting it over water. If you were collecting it in a syringe, right, then the outside pressure would affect the volume of the gas. You get my point? That's why probably he's not stated pressure as a control variable, because that is already controlled. If you're collecting it over water, then that is probably already under control, because you can't change the pressure if you're collecting it over water. But if it's a syringe that you're collecting the gas in, then the outside pressure would actually affect it. But even then, I think pressure should be the correct one. But over here, specifically related to the collection of gas, no, it's not stated pressure. But maybe we have to check the examiner report as well. Maybe they accept pressure. Okay, but is the temperature part clear?
Yes, sir.
Okay, and every time remember this, it's going to be the same exact pattern. It's going to be the same question. Now, the student plans to collect the carbon dioxide produced over water, draw a label diagram for the apparatus that we use to do these experiments, and should give an accurate recording of the carbon dioxide. I'll just give the market scheme option, which is this one. That this is where the barium carbonate and the hydroxide is added, hydrochloric acid. You're going to seal the container. There's going to be a tube, and that's where the carbon dioxide gas will be collected. The way you do this is always remember that you place a tube and then you tilt it so that this tube falls into the acid. You want to do that because you don't want to open the container at any one point. It has to be a sealed container. You place everything and then you sort of tilt the flask so that this particular smaller tube falls into the acid. That's it.
What about the syringe method?
In this, you can't use the syringe because they had specifically stated this. It was supposed to be collected over water, right? Is that clear?
Yes, sir.
And remember, there are. Make sure you go through this. That how do you collect gases? There are basically two ways: measuring syringe, a gas syringe, and over water. You bubble it through water, right? Or maybe an acid, or maybe an alkali, but something aqueous. You bubble it through it. There's another one which is upper delivery. That's for light gases, like you. But in that case, you wouldn't be able to measure the volume of the gas because you wouldn't be able to see the gas. There's going to be a transparent container with a transparent gas in it, so you don't know what the level is. And then there's a downward delivery as well, which is for heavy gases. And again, for that as well, you wouldn't be able to measure the volume of the gas. So which is why you're not going to use that. Is that clear?
Yes, sir.
So now this one again, another general question. State one weakness of the procedure of collecting carbon dioxide over water. What's wrong with collecting carbon dioxide over water? I mean, again, this is a very general question. What could go wrong? Like, why is it not suitable for bubbling carbon dioxide through water so you can collect it? Is carbon dioxide soluble or insoluble?
Soluble.
It's slightly soluble.
Yeah.
So the weakness in the procedure is that it is,
The solubility of carbon dioxide.
it's slightly soluble.
Okay.
So that would result in an incorrect value. And the change in the apparatus would be, the best change would be, instead of using the over water, use a syringe. That's going to be the change. So, one second. So use a gases, this one. And CO2 is soluble in water. Those are the two answers.
Yeah.
Then you're given these experimental values for each. So you've given the data now. And each time the volume of CO2 collected is given over here. And remember, the CO2 is coming from the carbonate. So the student uses the results to obtain an average volume of CO2 for each ore and records it in the table. So that's another reason why each ore is tested 3 times. Why do you want to test it 3 times?
Maybe you're trying to find an average and accurate result.
Get the precise reading results.
One thing is reliability. It increases reliability because you can remove anomalous values in this way. For example, I mean, repeatable values are kind of like if you do it one time, it's not a reliable result because maybe the first value is off by a big margin. For example, these values are very reliable. These ones are reliable. For iron, it's not very reliable because they're varying too much. So you might be making too many mistakes over here. Is that clear? So this average value isn't even reliable. Okay, let me just check if they're using the word reliability for this. Reliability, yes. Is that point clear? That's why you repeat values. Just to see, just to check if the values are repeatable or not. So for example, if I tell you someone to measure the length of a particular copy, and that's 9 centimeters, then another person comes at 9.1 centimeters, and then there's another person coming in and he says that it's 14 centimeters, right? So
yeah,
which value is unreliable?
14 centimeters.
So that's your anomalous value. So you can get rid of anomalous values in this way, and that's why you wouldn't be using them in your averages. So this one actually was unreliable. So one of the values is unreliable. Student made an error in processing the data to obtain the average volume of CO2 produced for one of the ores. State the error made by the student and calculate the correct value. So this one is the error that he made over here is he should not have used 55.
Yeah.
68 and 70 were fine, but 55 was way off. I mean, he probably made a mistake over here in the experiment. So the average should come out to be 69. It's not 64. Is that clear?
Yes, sir.
So the error is, what's the error? Student has used an anomalous result, and the correct value is going to come out to be 69. Is that clear as well?
Yes, sir.
And state the error. We did calculate the correct value. A second student suggested that the percentage of carbonate ions could be obtained by titrating the ground over samples with hydrochloric acid. Explain why titration would not be a suitable method. It would not be a suitable method if you titrate it because you won't be able to figure out the mass of the carbonate, because there's going to be hydroxide as well that would also be reacting with the HCl. So for example, if I got 10 moles of HCl reacting in a titration, I will not know whether that 10 moles is reacting with this one or whether it's reacting with the hydroxide. Is that clear?
Okay. Yes, sir.
So I mean, that's the point. With carbon dioxide, you're sure. If you're collecting the volume of carbon dioxide, you're sure that the carbon dioxide is all coming from this one. So if you got in this reaction, you got 10 moles of carbon dioxide, then you can be pretty sure that all that 10 moles is coming from barium carbonate, not from barium hydroxide. So that's a better method. Titration would not work, and that's what is the student. The acid will react with the hydroxide as well. That's so you will not know the moles of carbonate in that case. Next part is a bit of a moles question. 2 grams of this thing produces, no idea what that is the carbonate ore of manganese and does not contain hydroxide ions. So there is no hydroxide ions. So it's manganese carbonate, this one. The question is also given. So it's a simple moles question, 148 cm cube. So how many moles is that? Is it RTP? I think it's RTP. So divide by 24,000. So Munir, what's the number of moles for this?
Okay, is it 148?
Times 10 raised to the power -3.
And the moles of MnCO3 would be exactly the same, multiplied by the MR of this.
6.2.
You're getting how much?
6.2 times 10 to the power -3.
Grams?
That is 148. That is 148 divided by 24,000. Say.
Which one?
148
Okay,
divided by 24,000.
So that's
Yeah.
moles multiplied by the MR, which is what? Mn is 54.9. And you got 12, and you got 16 into 3, that's 48. So you're going to get what?
That's 12.
0.71.
71 grams, and that's out of 2 grams, right? So find the percentage of this thing. So you're going to multiply it by 100, and which would come out to be whatever the percentage is. It comes out to be. Yeah, I'm not getting this. 0.71. Are we getting 0.71? So this is 35.4%.
Okay.
Did we get this? Auntie, we got the same thing. So now the next thing is what's the next thing? State the measurements the students should make to determine the percentage of manganese carbonate in the sample of. State the measurements. No, sorry, a teacher suggested that the mass change from the thermal decomposition of a ground-up sample could be used to determine the percentage of carbonate in the sample. The teacher told the students to strongly heat a ground-up sample of the ore in a crucible. That's fine. State the measurement the student should make to determine the percentage of manganese carbonate in the sample. So the measurement would be the loss in mass. I mean, that would be the measurement. Like if the ore contains carbonate, let's say there is 10 grams, and then it would lose mass, right? When you heat it strongly, there's thermal decomposition that's happening. So the carbon dioxide would be lost. So there would be mass before decomposition, the mass after decomposition. I mean, that is the measurement that has to be. Sorry, the mass of the crucible has to be added as well. One second, did he talk about the crucible?
Yeah. Of the ore in a crucible there.
Okay, so it's going to be the mass of the ore plus crucible and then it would be the mass of ore plus crucible after heating. And the first measurement should be the mass of the crucible itself. So you'll be taking 3 measurements. After heating, before heating, and you're going to subtract the mass of the crucible from each one of them. That's how you're going to get the mass of the ore before heating and the mass of the ore after heating. And the next part is, how would you know that the results are accurate? Whenever you have a decomposition reaction, how do you ensure that the decomposition is complete? That heating is done till constant mass.
Yeah.
Is done till constant. Because if decomposition is not complete, every time you heat it, carbon dioxide will be lost. This would indicate that decomposition is complete, because if you heat it, there is no further decomposition. So that would indicate that the decomposition is now complete. So next one, an investigation. So that's question number 1. Now remember this, every time it's going to be the same exact pattern. It's going to be, so you have to practice a lot. You have to think about it, and every time it's going to be a different experiment. There's a lot of, I'll share you some notes about it, like collection of gases, what happens when you, and let me see if I mean, these minor points, like heating till constant mass, like whenever you decompose, everything has to be heated till constant mass. Let me check if there is one second. If I have an IT report on this. So practicals, 1 second. Those are two basics. I mean, the type of stuff you need is like basic raw experimental stuff that you should know. Like what is a burette used for? It's used for titration. How do you collect gases? How do you heat till constant mass to ensure? I mean, there'll be a lot of questions on heat loss. Like, how do you prevent heat loss? Put a jacket on top, put a lid on top. I mean, that's a source of error when you have experiments related to heating. As anyways, next one. Again, it's a question that you've never done before. So investigation is done. Now this one is, the previous question was more about design. It's more about finding errors with the design of the experiment. It wasn't about calculations. It was more about that the data you collected, what's wrong with that. So it's more about finding faults with the experiment. The second question is, an experiment would be given and the values would be given, and you'll be asked to do calculations or analyze that. So the first one was about planning and design, and this one is more about analysis. And every time the second question is about analysis. So he says that an investigation is done to find the percentage of copper in a brass nail. The brass nail is dissolved in nitric acid, and the resulting solution is diluted with distilled acid. Copper ions are formed in this reaction. So whatever that brass nail had copper ions. Use the electrode potential to write a balanced ionic equation for the reaction between copper and concentrated nitric acid. So nitric acid is the higher potential, so it would definitely gain electrons, and copper is the lower potential, so it would I mean, this one, it would lose electrons, right? So, and this should be multiplied by 2 so that the electrons are equal. So it's going to be 2NO3 minus 1 plus 4H plus 1 plus Cu, and my products are going to be CO2 plus, and at the bottom there's going to be a 2NO2 and there is 2H2O. Now, a balance accurate of 2 decimal places was used to weigh a small beaker, and the mass of the beaker recorded. The brass nail was placed in the beaker and the mass increased by 3.76 grams. Calculate the percentage error in measuring the mass of this nail. So the brass nail was placed in a beaker, and the balance was accurate up till 2 decimal places, and was used to weigh a sample of and was used to weigh a small beaker, and the mass of the beaker recorded. So what is the percentage error? You're going to take 2 readings, right?
Yes.
Now remember, it's accurate up till 2 decimal places, right?
Yeah.
So when you take a reading, what happens? What's the error? It's the error is the
Plus or zero.
it's the minimum graduation
Mhm.
divided by 2.
Yeah.
Like when I say, like when I'm taking a reading and there's this mark and there's this other mark, right? And there's this other mark. Let's say this is 1, this is 2, and this is 3. And there is no graduation in the middle, right?
Yeah.
So when the value is over here, I'm going to call that 2, right? Because I can't, so yeah, I'm going to call that 2. I'm going to round it off to 2, right?
Mm.
Is that clear? Like if you have a thermometer and that's the minimum graduation you have. So
Yes, sir.
you're just going to refer to as 2. 2 is anything that is from this point till this point, that's 2. Is that clear?
Yes. Yes, sir.
So 2 is basically plus minus
0.5.
0.5. So anything with that range, because the value is never going to be exactly 2. Sometimes it's going to be slightly higher than 2, sometimes it's going to be slightly lower than 2. Now, the same happens with this with this reading that if you take a value, let's say you take 3.76, then this 6 over here, the minimum graduation is 6, right?
Yeah.
It could have been, I mean, what would it be? It would be plus minus 0.005.
5.
Like the smallest graduation, the
yes.
smallest graduation divided by 2. Like over here, the smallest graduation was 1, right?
Yeah.
So you're going to divide it by 2. It's plus minus 0.5, right?
Yes, sir. Okay.
Over here, the smallest graduation is 0.01, and you're going to divide by 2. So it's going to be plus minus 0.005, right?
Yes, sir.
But in the marking scheme, it's going to probably take it as 0.01. And let me just check and confirm it if it's taking it as 0.01. And I'm going to explain where's the accuracy question. Did he? That's 2D part 1. He's doubling it. So I'm going to explain. So he's doubling it. He took it as 0.005, but then he doubled it. But first thing, is this clear that whenever you do a reading, whenever you take a reading, and when you say it's 2, it's not actually always 2. It's either 2 plus minus 0.05. So it's the minimum graduation divided by 2. Is that clear?
Yes, sir.
Now, in this case, the minimum graduation is 0.01. So you're going to divide 0.01 by 2, and it would give you 0.005. But why are you then multiplying it by 2? So remember this, the reason you multiply it by 2 is, if you're measuring this, the mass increased by 3.76. Are you taking 2 readings or are you taking just 1 reading? How do you measure that the mass increased by 3.76? Like you should have, I mean, you're going to take 2 readings, right? I mean, let's say the first time the mass was 10 grams, right?
Yeah.
And then how did you figure out that the mass increased by 3.76? You did another reading and the mass came out to be 13.76 grams, right?
Yes, sir.
So basically you're taking 2 readings and then you're subtracting those 2 readings. Is that clear?
Oh, yes, sir.
So the first reading will have an error of 0.005. The second reading again will have an error of 0.005, right? What happens to errors in physics if you add or subtract? The errors get added up. So if you were to calculate the mass increase by 3.76, you're actually measuring 2 masses. The first one is without the brass nail, and the other one would be with the brass nail, and the mass would increase by 3.76. The first reading will have an error of 0.005. The second will also have an error of 0.005. That is the smallest error, but since you're subtracting 2 values, that error in addition subtraction will get multiplied by 2. So it's going to be 0.005 multiplied by 2, or it's going to be the error is going to get doubled. Divide by the mass. How do you calculate the percentage error? It's the value divided by the error divided by the value into 100. Is that clear?
Yes, sir.
I mean, I'm just assuming you know physics.
Just a bit.
So let me just I'll just clear this point about errors, especially about subtraction. And remember, it's always the smallest graduation divided by 2 in one value. So for example, what is the error in a burette reading? Like if I tell you, if I show you a picture of a burette, so let's say you've got some burette value. Let's say this one. If you can see this, what is this value over here? I think this is you always read the lower meniscus, right? So I think it's 42.3, right? Is that clear? Maybe let's do it a bit more accurate. Let's take this one for a second. Remember, in a burette reading, you always read the lower meniscus. So this one is 19.7, right? Is that clear?
Okay, yeah.
I said this is coming out to be 19.7. So I'm just giving you an idea that if this is 19,
Okay.
I say if this is 19.7, plus minus what? What's the error? The error is the smallest graduation. What's the smallest graduation in this case? It's 0.1, right?
Yeah.
The smallest graduation, because this is 19.1, this is 19.2, 19.3. So the smallest graduation is 0.1. So since the smallest graduation is 0.1, the error would be 0.1 divided by 2. So it's going to be 0.05, right? It's going to be 19.7 plus minus 0.05. Is that clear? And when you add and subtract two values, the errors, they get added up. So make sure you remember that as well. Adding or subtracting values, the errors get added up. So make sure remember that part as well. So any device, smallest graduation divided by 2, whatever the smallest graduation is. So if I go back to this question, the smallest graduation over here was 0.01. I divided by 2, I got 0.005. But since I was calculating this, the only way I can measure the mass increase is that I subtract two values. So whenever I subtract two values, the errors are going to get added up. So the error would be twice. The error in 3.76 is going to be double the error in one value, because I'm subtracting two values. And how do you calculate percentage error? The way you calculate percentage error is, in a particular value is the error divided by the actual value into 100. So in this question, the error was 0.005 into 2, and the actual value was 3.76, I think, and in 200.
Yeah.
Is that part clear?
So 376 or 376? No, 375.
3.76.
Okay.
That was the actual value. The error was 0.005 into 2. As the next part is 50 cm of nitric acid was added to the nail in the beaker when the reaction finished and the nail had dissolved. The solution was transferred to a 250 cm3 volumetric flask along with the washings. The solution was made up to the mark with distilled water, concentrated nitric acid. State one precaution related to this hazard that must be taken when using. Just wear gloves. Wear gloves, goggles. So the spray, acid spray, does not fall into your eyes. And so just wear gloves and goggles, that's it. The next part is a calorie meter can be used to determine the concentration of metal ions in solution. When light passes, calorie meter measures color. So again, you've never studied a calorie meter, so I mean this is the first time you're hearing about it. But don't get worried about that. Don't get worried about it. I mean, calorie meter is not even in your course. It's but remember all the answers you're going to find the answers from the same question. So it passes through the solutions of metal ions. Some of the light may be absorbed. So what is happening is there's a solution and it's got a bunch of ions and light passes through it. And by measuring the amount of light that is absorbed, when light passes through it, some might be absorbed. So the calorie meter would measure that, and that would give you an idea about the concentration of the ions. The quantity of light absorbed is called the absorbance and is measured by a calorie meter. The absorbance of solution of known concentration of copper-2 ions can be used to determine an unknown concentration of copper-2 ions. So he's saying that you can compare it. You can compare the absorbance of a known concentration. Like if you had more particles, this would be more absorbance. If you have less particles, you would have less absorbance. So by comparison, known concentration of copper-2 ions can be used to determine the unknown concentration of copper-2 ions. So for example, a 0.1 mole per dm cube copper-2 ion concentration solution had an absorbance of, let's say, 2.5. I don't know what the unit is, but the absorbance is 2.5. So if the concentration decreases 10 times, the absorbance would also decrease 10 times, right? Is that clear?
Yes, sir.
So if my absorbance is now 0.25, that means the concentration of my copper ions is 0.01 mole per. So that is what he's saying, that you can compare it with the known concentration, the absorbance of a known concentration, and you can use ratios to figure out the concentration of the unknown solution. So the question is, calculate the mass of copper-2 nitrate needed to prepare 100 cm3 of this solution. So just moles. What is moles volume into concentration? That's 100 over 1000 into 0.8 mole per dm cube. And that would give you 0.08 moles, right?
Yeah.
And you have to find the mass of copper-2 nitrate. So 20.08. Mass would be moles multiplied by MR, which is
MR,
which is 63.5 plus NO3 twice, that's 124. That's copper nitrate. So you'll find the mass. We'll just have a look at the mass. It's coming out to be 115 grams. That's it. But anyways, moving on. Here's a table now. You don't even need to study all of this. I mean, the shortcut to this question is don't even look at that. What he's asking for is, I mean, this is not given. Volumes of point are diluted with distilled water to prepare a series of 10 solutions of different concentrations. So, and the absorbance is measured. Now, the total volume needed of each solution is 20 cm3. The absorbance of each solution is recorded by a calorie meter. Complete the table to show the volume of 0.8 mole per dm cube and distilled water needed to prepare each solution. So the first one had a concentration of the first solution. We're going to start with 0.8. Which one has a concentration of 0.8? No one actually. So let's say copper-2 ions 0.8 mole per dm cube. So we can discuss serial dilution in the next class then. You can have another one. We'll talk because this is going to take a long time now. What we can talk about in the next class is, this class, what we have done is safety precautions. If you practice a few, you'll know what the safety precautions are. They're pretty obvious. We have discussed a bit about errors. Make sure you remember this. That error in any apparatus is the smallest graduation divided by 2. Like any apparatus you take. If the value is if for example in a burette the value is 19.7, the smallest graduation is 0.1. So that means the error is 0.1 divided by 2. And if you add or subtract values, the errors get added up. So every time the error is going to get added up. How do you calculate the percentage error? We learned about that as well. We learned about the fact that we talked about constant mass, that whenever you heat a substance or decompose it, it has to be done till constant mass. That ensures that the reaction is complete. Then we learned about, the other one was more of a general question. We talked about the reliability of the values. That why do you repeat experiments? So that you can figure out anomalous values. You can remove anomalous values. You're not going to averaging values gives more accuracy. But the first part is you're not going to include anomalous values in your expression. So let's continue with serial dilution. That's another important thing. So we can talk about serial dilution, but make sure you remember these points that we studied in this. The other papers would be exactly the same. It's not going to be that different. Serial dilution pretty much comes in almost every one. It's the same constant mass, same errors, same everything is kind of the same. The rest is more of a general knowledge question, like you have to figure out by reading the question. So let's continue next time then. Okay.
Thank you, sir.
Yes, Sam.
Thank you so much, sir. We have appreciated.
Okay, take care. Bye.
Thank you.